Everyone, so today we are going to discuss about the decision making video on how the crystal defects will affect the performance of solar cells and LED and microchips performance. Okay, so actually what is meant by crystals? Regular arrangement of atoms and molecules in three-dimensional space. Okay, so this is called as crystal. So for a regular crystal, it has regular arrangement. So in real life, so there is a defects was occur in every crystal. Okay, so based on the crystal defects, so we have many types of crystal defects. Okay, so point defect, line defect, and surface defect. So these defects occur in every crystal structure. So it will affect the performance of the every applications. Okay, every electrical and so it will change the electrical and optical properties and etc. Okay, so today we are going to detailedly discuss about how it will affect the performance of LEDs and solar cells and microchips performance. Okay, so let's start now.
Types of crystal defects. Point defects. These involves one or few atoms. Vacancy defect. A lattice site where an atom is missing. Interstitial defect. An extra atom occupies a space between regular lattice positions. Substitutional defect. A foreign atom replaces a host atom. Frenkel defect. An atom leaves its lattice site and moves to the interstitial position. Schottky defect. A pair of missing positive and negative ions in ionic crystals. Line defects. These are called dislocation and involve a row of atoms. Edge dislocation. An extra half plane of atoms inserted in the crystal. Screw dislocation. Atomic planes shift in a spiral manner around a line. Surface defects. These occur over a surface area of the crystal. Grain boundaries. Boundary between two differentially oriented crystals. Twin boundaries. Mirror image crystal regions. Stacking faults. Irregular stacking sequence of atomic planes. Volume defects. These involve larger regions of the crystals. Voids, precipitates, cracks, inclusions.
Okay, very good. So this is on the types of defects. So we have four types: point and line and surface and a volume defect. Totally we have four defects. Okay, so line defect is the two-dimensional, one-dimensional defect. So the surface defect is the two-dimensional defect. Volume is the three-dimensional defect. So Johnny deeply explained how many crystal defects was there. Okay, so next we move on to solar cells.
Effect on solar cells. Most solar cells are made from crystalline silicon. When sunlight hits silicon, electron hole pairs are generated. These carriers move towards electrodes. Electric current is produced. Crystal defects act as the recombination centers. This means electrons recombine with holes before reaching electrodes. Current output decreases. Efficiency reduces. In polycrystalline solar cells, grain boundaries especially increases recombination. Higher defect density gives lower efficiency and reduced power generation. Even small increase in defects can reduce solar panel efficiency by several %.
Okay, good. So next, applications of solar cells.
Now let us discuss the applications of solar cells in rural agriculture. A rural village faced frequent power cuts and high diesel costs for irrigation. Farmers struggled with low crop yield and increased expenses. Solar cell based water pumps were installed as a solution. Solar cells convert sunlight into electricity using photovoltaic panels. The pump provides reliable daytime irrigation without fuel cost. Operating expenses reduced by nearly 70%. Crop productivity and farmer income improved. The system is eco-friendly with zero carbon emissions.
Okay, good. So next we move on to LEDs.
LEDs are commonly made using gallium nitride. So how LEDs work means electrons recombine with holes and energy is released as light. So when defects are present means non-radiative recombination increases. Energy is lost as heat instead of light. Brightness decreases. Device temperature rises. Lifetime reduces. So high dislocation density in gallium nitride crystals reduces luminous efficiency. So more defects equal to dimmer light and more heat loss. This is why advanced crystal growth techniques are used to minimize defect in LED manufacturing.
Next, applications.
The application of LED, mostly this is used in home lights and TV and display. Uses of LED TV display digital and traffic signal, yellow, red and green signals, mobile phones and laptops, automobiles, headlights, brakes, lights and indicators, decorative festivals and serial lights and decorative lights, medical equipments used in medical instruments and devices, and emergency lights in forests.
Okay, good. So these are all the applications of LEDs, right? So next we move on to microchips.
The effects of microchips. Microchips used in ultra-pure single crystal silicon wafer. Inside microchips, billions of tiny transistors operate at the nanometer scale. In the defects present are leakage current increase, carrier mobility decrease, switching speed reduce, transistor reliability decrease. In nanoelectronics, even atomic level defects can cause chips failure. More defects is equal to low performance and reduced manufacturing yield.
Okay. So now conclude that. So these are only defects. So how the defects will affect the performance of solar cells and LEDs and microchips. So defect is the very tiny type of disorderness. Okay. So it will affect the overall performance of the materials. Okay. So it will affect the electrical and optical performance and etc. So now we discussed about how the defects will affect the electronic performance. Okay. Thank you.